Hey guys, I guess this is our first video launching into this idea of class reversal. Just a reminder, I need to have notes from these videos along with the outline that I will check the very next day in class. So make sure you have notes from the videos done. I'm going to try to keep the videos relatively short and to the point. Please also remember the pros as opposed to the cons. Use the advantages liberally. Make sure you go back, rewind whenever you get stuck, go back and pause to write things down. Take a break if you need to in the middle of a video. Pause it, go do something, grab a snack, come back, finish it off. Also remember you can access these anywhere you can get YouTube or the internet. Along with if you come in before or after school, especially after school though, I've got to make the videos of course. Bring a flash drive, I'll drop them on there and you'll be good to go. Anyway, G.1 is a whole bunch of state defines, memorize, talk about, discuss, blah, 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 not any problems whatsoever. So I'm not going to spend hardly any time on it. All I want to spend time on though are the concepts of the laser, okay? So I'm going to talk about the laser. Please do not forget the other states and defines. For example, you have to be able to state the range of, I believe it's wavelengths in this section, for all the different areas of the EM spectrum. You have to know the range of wavelengths for visible light. You have to know the range of wavelengths for the X-ray region. You have to know all of those wavelengths. So please make sure you go back and look at that. Anyway, lasers. Before I start talking specifically about lasers, let me pull up something that you have seen in the past, specifically this guy right here. And I showed you this with the Bohr model. Yeah, let's play and actually let things start going. So this is a Bohr model of a hydrogen atom. We talked about it is a good simplistic way of looking at atomic structure. You have an electron, goes around a nice little circle, right, around the nucleus. Whenever it is given some energy, the electron jumps from the lowest energy level, which it's in now, to a higher energy level, like it was a second ago, it is now again. Okay? But immediately, or soon thereafter, it tries to release that energy, and it releases that energy in the form of a photon, okay, in the form of a photon. So it jumps up, releases back down. Over here on the right-hand side, you kind of see an electron energy level map of what's going on. So right now it's in 2, and then it drops down to base level 1. Now this is white light coming in, meaning it has all the different colors, each with all different types of energy, right? The closer you get to the infrared region, let's go ahead and pull this up. The closer you get to the ultraviolet region, the higher the energy, and down past red into the infrared region, the lower the energy. Okay. Now, here's the part that I need you to remember. When an electron is in an excited state, it will drop down from that excited state to a lower energy level and give off a photon that is worth the exact same amount of energy as the drop. Okay, so for example, going from N4 all the way down to N1, like it did a second ago, right, all the way up to the 4th energy level, all the way back down to the 1st, it will emit a photon worth the energy drop from N4 all the way down to N1. And we calculate how much energy was released by looking at the photon, right? The photon is worth that amount of energy. And the energy of light is equal to h, which is Planck's constant, times f, the frequency. Now that's not critical for you to understand. What I have to have you get though is whenever an electron drops down an energy level, it emits a photon, okay? And that photon is worth a very, very, very precise amount of energy, right, because of its drop, which leads to a very, very, very precise frequency of light being emitted. Okay, now, on to discussing kind of more a little bit about lasers. All right, so what basically happens with a laser is I have a whole bunch of a certain type of atoms. Sometimes we use a combination of atoms. But for now, let's just talk about a helium neon laser. That's helium and neon in it. It really doesn't matter the type. All of them behave in a similar manner. The reason we have different types is because we have to find the just right energy drops. Anyway, basically, you have an atom, right? Here's the nucleus. Don't really care what's in the nucleus right now. And then you have the simplified understanding of orbitals. Now, I'm going to give all the electrons. Let's just take helium, for example, which has 2 electrons. That would be in the first orbital. It's the first orbital can hold 2 electrons, the next one 8. But anyway, I give the helium a little bit of energy, and that energy is normally directed to the electrons, and so those electrons will end up jumping up to, let's say some higher energy level, depending on how much energy I give them. Okay, depending on how much energy I give them. Right? So now they're up in this higher energy level. Now normally the electrons want to immediately fall back down. Now if they do, they give off light, and it doesn't really do me any good. Okay? I need to put them in an energy level that they can hang out in very well. So maybe I've got to give it a little bit more energy to get them up into, let's say, the 3rd ring, or the 4th ring. Basically, I need to get them up into a metastable state. A metastable state. Metastable. That is nowhere close to the right spelling while I'm writing and trying to think about things. Let's actually write stable. A metastable state. What that means is the electrons can hang out in that energy level just fine for an extended period of time. They don't immediately want to drop down. They're not completely stable. They're in a metastable state, meaning they're mostly stable, if you will. They can hang out there for a long time, but eventually they're going to want to come back down to the ground level. Okay, so I need to get electrons into a metastable state. So I give the atom some energy to get the electrons into a metastable state. Now the second thought is, I do that with one atom, but that's not enough. You know, a laser is going to consist of a whole bunch of things, right? And you've got all these atoms in a tube here, right? All these atoms in a tube, and here's my focusing lens, if you will. So I've got all these atoms in here, and if one of them has its electrons in a metastable state, so what? You know, that's 2 electrons. If we're talking about helium, just 2 electrons that has excess energy that it's ready to give off. That just doesn't matter. I've got to, instead of just getting 2 electrons, I've got to take over 50%, hopefully well over 50%, up into this metastable state. That's population inversion. Population inversion. Okay? You get more of them into the excited state. You get more electrons for all of these atoms. All of these atoms over here. You need to get more of them up into the metastable state than I had down at the baseline. So I try to get more of them up. So I keep pumping energy in, to get more of them up. The third and last step is called stimulated emissions. Stimulated emissions. Okay? What that means, and this is kind of a weird phenomenon. Let me come back and redraw my helium atom. Right, I had my nucleus, and then I had rings around. Okay, and I already have the electrons excited into their metastable state, and I just drew for the sake of just drawing. I drew those electrons in the second orbital. And we call that the metastable state. What happens here is they're going to drop back down naturally, some energy level here, some energy here, and give off some frequency of light, F. Okay? Now, they're going to hang in that metastable state for a very long time. But the odd part, if I put a photon of light, that has the exact energy worth as the energy drop that the electron is going to go through. What that means is that photon of light has the exact same frequency as the photon of light that the electrons will give off whenever they drop down. If I put that guy through that atom, run it past those electrons, oddly enough, when the electrons drop down, and by the way, let me backtrack. It's not when they drop down. Whenever the photon goes by, here's kind of the odd part, it causes them to drop down. Right then and there, instantaneously. It causes them to drop down, both emitting their own photons here. And since they're both dropping down, at the same time that guy comes by, they're going to be in phase. So I put in an electron, or I put in a photon that has the same energy as what's going to happen as the photon that's going to be emitted once it drops, right? And thus the same wavelength and frequency of light comes out. Also, because of stimulated emissions, whenever, this is the whole stimulated part, right? I'm putting the photon in, I'm stimulating the electrons to drop, which then causes the emission of the other photons, right? Because it happens right then and there, they are also in phase, right? Which gives me the laser, which is monochromatic and coherent, right? Monochromatic and coherent light. Focused, by the way, that's the lens cap up there, but never mind that for now. Monochromatic coherent light gives me a laser. Now, this can only be done with very specific items, set in very specific ways to get this kind of focused light being monochromatic and coherent. So to kind of refresh here, spelling stable correctly also, the first thing you have to have a metastable state. Okay, you have to have the electrons given enough energy to get up into their metastable state. Now understand, this is a simplified way of going about it. That's okay. Get the electrons up into a metastable state, up into some higher energy level where they're mostly stable. 2, population inversion. Well, I just don't have one atom that I'm doing this with. I have moles of atoms that I'm doing this with, more than likely, right? Moles of atoms. Lots and lots and lots and lots of them. I have to have more of them in the excited state than in the ground state, so population inversion. Then, since now I have more of them up than down, I'm going to send light in, monochromatic, mind you, light in that has the exact same frequency as the frequency of the photons that will be emitted whenever the electrons drop from their excited metastable state to the ground level. Okay? They pass by, and whenever they do, the electrons are stimulated, if you will, to drop down. I cause it by putting the light through. They drop down whenever another photon comes through, emitting photons themselves. That, because I had the frequency already lined up beforehand, has the same frequency, and the really cool part is, it is coherent, meaning it is in phase with the photon that I set in beforehand, thus giving me out a monochromatic, coherent light source, right? Monochromatic, coherent light source. Giving us kind of this amplification idea of all the electrons falling at the same time, right? Giving me a very intense burst of light. This is also, by the way, one of the main reasons, this kind of concept, that lasers were initially only pulse lasers. But by the way, lasers really aren't continuous that much. For the most part, they are all pulse. Now, we can go very short pulses, femtosecond lasers, for example. Be a very, very short wavelength there. Short pulse between them. But never mind that here. For the most part, pulse, because of this idea, right? I've got to then repeat the process. I've got to recharge the laser. I've got to get most of my population back up into the metastable state, and then I can send another little bit of light through, then drops them down, giving me one intense burst of light. All right, anyway, that's kind of the idea with lasers. We'll talk a little bit more about that tomorrow. I figured that was the most complicated idea, so I wanted to go ahead and head a little bit of that off while you're doing your outline tonight. Don't forget to watch the next video over GTube, and I'll see you tomorrow.